Okay, today we're going to be looking at nuclear magnetic spectroscopy, NMR spectroscopy, which is a very useful tool we use in the organic world to look at or help us determine if you were successful in making a particular organic structure. Typically, it's safe to say we can use an NMR to tell exactly if we actually made what we wanted to. And you can actually, with the right NMR and the right skill, actually tell exactly how a molecule is put together down to the minuscule little detail. All right. The other plus it has going for it is that we are actually able to use very small samples, and the sample's never really destroyed. Because when we actually do an NMR, you are actually just putting a test tube in it, and the only thing that the sample is subjected to is magnetic fields and possibly RF, radio frequency, so electromagnetic radiation. Now, in the real world, we typically use this in conjunction with other instruments, kind of like IR to help us identify the functional groups ahead of time, or mass spec to get the actual molecular weight. But you actually can do everything with just an NMR. Which is good because it's by far the most expensive instrument we can really get in an organic lab for the most part. Okay, now in NMR, and what makes it so versatile is these first two atoms it's really good at studying. So just straight protons and carbon, which are two things that we're going to find in any organic molecule, guaranteed, because that's kind of all they're made up of. Now where this comes in very handy is proton NMR. That earliest one is by far the simplest way, and so what that translates to is we really can study every single hydrogen in a given molecule and see how they're different from each other, because we will see that a hydrogen, say, attached to a carbon shows up totally different than a hydrogen attached to an oxygen, and you will see it is even shift based on other things it's attached to. Now, the other ones are just kind of neat little things we can do. It turns out as if an atom has an odd number of electrons and neutrons combined, you can study it in a type of NMR. You just have to actually change the frequency that you're studying, or the radio waves that actually come off of it. But if you hear the phrase NMR, and it just says NMR, that is assumed to be proton NMR, so it is studying just hydrogen. Because if I do want to study the carbons in a particular molecule using NMR, I use carbon NMR, and that's what we do call it, is carbon NMR. All right, so let's look at what this means and what's going on with this. All right, so here's a neat little effect that helps us out in this world, or that subatomic world that's in our large magnets for the NMR. So back in Chem 1 and Chem 2, we talked about our quantum numbers for our electrons, and we talked about one called the spin state. We said that the electron had a particular spin. Well, it turns out that quantum spin is something shared by our protons and neutrons in the nucleus. So each one of those has an individual spin. What happens as that thing spins, it creates a small amount of current as it goes through that, and that creates a small magnetic field. So just the nature of a nucleus spinning creates a small but noticeable magnetic field, and we're going to be to take advantage of that to study what's going on with the hydrogens. Now, how are we going to study that? Well, we're going to take advantage of a cool little thing that happens when you put those atoms in a magnetic field. It turns out that a magnetic field that should be generated by the atom, or by those nuclei, those spinning nuclei, it will line up either with or totally against the magnetic field. It's either going to be totally with it and actually help almost like you'd predict, where the north end of a magnet's lining up with the south end of the magnet, or it's perfectly opposite. But it's never in between. It's either going to go one or the other. It's either going to go to that high spin or low spin. And we actually can call this low energy and high energy, which kind of makes sense. It seems like it would naturally want to do this where the magnets actually cancel each other out. And we do see that that's actually more stable. All right, but it does one or the other in any magnetic field. Now, where this comes in handy for us is the fact that we have a lower energy state and a higher energy state. All right, so put a bunch of these in a magnetic field, and we get a distinctly different level here. Now that's totally different than outside the field. Outside the field, the poles are going any direction they possibly want. So any magnetic field that would be influenced by that is all going to cancel out. So all of these atoms have the exact same energy in them. But when I put it in that magnetic field, we can see that the energy of a spin in phase with the magnet would be totally different than one that's going against the magnetic field. So we actually have two totally different energy states. Now, the neat thing is, unlike maybe what we'd say in quantum theory, where our atoms are always going to choose to go into the lower state, turns out inside that magnetic field, the energy that the atom is going through causes our nucleus to flip back and forth between these two states. That's what we're going to see comes off, or that's what we're going to study in an NMR. So that flipping back and forth that happens naturally is creating a resonance, and it is going to go back and forth. It's not like it just goes up and then back down. It actually goes back and forth because this is a way for the atom to absorb and release energy. Now, given enough time, it's likely to believe they will all go to lower energy states, but they won't necessarily stay there because this is a very small amount of energy. It's very easy to put this back into the molecule. Temperature will sometimes do this. Even other radio waves. And we did say this is inside a magnetic field. Just by moving the atoms from outside the magnetic field into the magnetic field, you're going to start this resonance cycle to happen. So as long as we start it, we're going to see it go back and forth until it releases back into a steady state. But that resonance is what we're going to see. Now, technically, that resonance is actually releasing energy. It's just based on the energy level difference between those two states, and going back and forth releases a very particular energy. Now, where this comes in handy, the size of that energy difference is proportional to this B, which is the magnetic field. The larger the magnetic field, the larger this energy difference is. And we find something neat. If I actually stop and back up and look at this, and then really just look at what the frequency is, we find that an electromagnet, or a slightly larger magnet than what we find in, say, like a refrigerator magnet, the frequency is in the megahertz to hertz range. So this frequency is in the radio wave range. So what comes off, what's actually kind of neat, is if you get a atom resonating between these two states and going through that, it's going to give off a particular radio frequency. And it is proportional to that size of that magnet. All right, what do I mean by that? All right, the magnet size does vary. Both of these are just some old classic ones, but these magnets are really ridiculously big. I mean, you get an idea that this thing is technically bigger than whatever size this actual window is. And this one, I actually do think that these tiles down here are kind of like typical linoleum tiles. So these could be 1 inch by, or 1 foot by 1 foot. So these are really big units. But it makes sense they would be. These are very, very powerful. So 0.9 Tesla and 1.8 Tesla. To put that in perspective, the magnetic, if you ever see the videos where they pick up a car with a magnet, those electromagnets are typically not much more than 1.2 Tesla, and that's enough to pick up a car. So these are ridiculously powerful. Now, the only thing different between these older style and the more modern one is we've gotten a lot more efficient at making the magnets, and they're a lot more precise in what they do. So it might not so much that the 80 megahertz or 40 megahertz is more in tune, it's more that it stays that way a lot more, so more significant figures. Now, the numbers here are kind of interesting. If we are actually determining magnetic strength, we typically see them measured in Teslas or potentially Gausses, because that's related more to the forces between those two metals when we use a magnetic field. But when we actually look at NMR, since what we really care about is that resonance of it, this is actually the frequency for a hydrogen atom in that magnetic field. So 40 megahertz versus 80 megahertz. If we go up on the size of the magnet, we will increase the frequency. But just to put this in perspective, a modern NMR that we could get for almost any school This is a SpinSolve 60. They make SpinSolve 40s and 80s. And I have this picture to show you the size of it. These are pretty small little units. And even though this is 60 megahertz, which is exactly the same, or in that range between these two, this thing is far superior to those previous ones. And it really has a lot to do if we figured out how to make these better. It's just a much cleaner magnet, a lot nicer electronics, much better way of picking up the radio frequency. So you get a lot better results. Now, and this one actually, see down here it says phosphorus. It's able to actually determine the phosphorus ions that we were showing on that previous page. It'd not necessarily be one that we'd use for the average organic chemistry lab. We'd either want it just to be a proton one, and on SpinSolve that doesn't list anything because all of them will do protons. But if we had one, we'd probably want one that said carbon here because that's a little bit more versatile for the general organic lab. All right, but we don't have one of these because they're awfully expensive. All right, now here's where this comes in handy. The reason an NMR is so versatile is that frequency I was just talking about, so that maximum frequency of 60 megahertz, that's that ballpark range for where we would find the average hydrogen in that particular field. But that average hydrogen would be a hydrogen that's maybe surrounded mostly by things that are equal in its electronegativity. So what I mean by that, if we were to look at something like a carbon-hydrogen bond in methane, because the electronegativity is about the same, or the electronic structure around the hydrogen is very close to what we get for a raw hydrogen, we would expect to see this close to that 60 megahertz in frequency. So this is going to resonate right around 60 or so. All right. But if I look at the same type of hydrogen, but it's attached to, say, an oxygen, the oxygen being a lot more electronegative is actually pulling more of those electrons towards it. So this hydrogen is less protected by those electrons. And we see something neat. Even though the radio frequency waves that are coming off this are because of the hydrogen spin and how that nucleus's spin state flips from one direction to the other, the electrons around that hydrogen protect it from that magnetic field. They kind of create their own magnetic field. So those, the more electrons we have, the more shielded it gets. Well, this one, because of that electronegativity difference, this hydrogen has fewer electrons on it. It's de-shielded. So we would expect its frequency to be slightly higher than 60. And I am just going to say that, just say higher. And we're going to see that those electrons, because they're quite variable in how they can be a hydrogen, we're going to see a lot of different splits or a lot of different shielding aspects. And the degree that we actually see it change has a lot to do with the size of the frequency. Well, now what I mean by that, you know how we showed that as we went up in magnetic field, the overall average frequency went up? And I had something like this. If we look at this, 60 megahertz at 1.4 Tesla, or 80 megahertz was 1.8 Tesla. I'm going to write those two numbers down. So if this was 60, then this was 1.2. If this was 80, this is, was that 1.6? 1.8. All right. Well, what also changes is this de-shielding. So while this is just slightly lower at 60, it's going to be slightly more lower when we go up to 80. So if you think about those two things being different in their peak and their distance in frequency, as we go up, that distance gets even more. It's going to help us isolate and identify those individual frequencies because we got a larger range. And just because of that, since that goes up with magnetic field, we find that the professional or the more advanced NMRs really are designed about the most powerful magnet you can possibly get. So while we just saw 40 megahertz magnet and 80 megahertz and then finally a 60, none of those are anywhere close to the top of the line. So top of the line, probably a few $1 million and quite a bit upkeep, is this nice little thing from Brooker, which is 1200 megahertz. They actually call it a 1.2 gigahertz because that's how cool it is. 28.2 Tesla. If you have a metal limb and you walk into this room, you're probably going to get sucked into the magnet. This is the type of thing you are very careful around it. that is a big factor as to why this platform is actually made out of wood. Because if it was made out of metal, that would have been hard to install. That is a ridiculously powerful magnet. Has to be cooled with liquid nitrogen and liquid helium. But it is something that's maintainable. Matter of fact, there are a few places that you actually come across magnets, maybe not this big, but MRIs are very powerful magnets, and people get inside those things all the time. So being around this big of a magnetic field isn't that bad or dangerous. You just have to take precautions. Okay, so we say we want these large voltages. What are we talking about this splitting and what causes it? I mentioned electronegativity, but that's not all. That shielding is related to the electrons around it. And while electronegativity will actually help us predict this, it's much better to point out that the shielding has a little bit more to do with the electron structure as a whole. So the entire electronic structure. So it's not just that there's an electronegative nearby it, it's the type of electron cloud nearby it as well. So we will see pi bonds affect it differently than sigma bonds when they're adjacent to it. So we're just going to say it's the electronic structure. So we're going to see a couple things that pop up here that actually add to this diversity and complexity. The number of absorptions, or the points on that scale, are related to the equivalent protons. Sometimes it's actually the sheer number of protons, but more often than not we have ones that behave the same. What I mean by behaving the same, if we have on the end of the molecule something like a CH3, all those three are going to behave almost the same because there's nothing really different about them. So that, even though there's three hydrogens there, they would only create one peak. All right, so let's look at what I mean by that. All right, so I have a relatively complex molecule. It has hydrogens here, here, and here, and they are circled for a reason. They are chemically equivalent. Now, when we say chemically equivalent, I want us to back up. I'm going to redraw this molecule to something we learned in Orgo 1, which was what would happen to, say, this molecule if we were to try to actually do free radical halogenation. Now, I'm going to actually do free radical chlorination because chlorination actually had a lot more options. Because if I did this particular molecule with bromine, we'd pretty much have put bromine here because that particular location is secondary. But if I do chlorine, then all of a sudden my primaries would happen as well. And on this one, we would have no problem expecting that you might put a chlorine here, or on one of these locations. Now, you wouldn't have to worry about two different products related to this because if you put a chlorine on that first one, it's the same whether you put it on, it's the same regardless of which hydrogen you replace. So this particular molecule only makes 3 monochlorinated products. All right. Those monochlorinated products are kind of the same as saying equivalent hydrogens. So since there were 3 potential products, we actually get 3 potential peaks. All right, now what's going to be a challenge is sometimes trying to predict how many signals there actually are. So we're going to look at a few of these and see if we can make sense out of it. As I go across, I want to actually try to identify the ones that are based on the most shielding and actually leave them kind of first. And for the most part, the ones that have the most shielding, the ones going to be furthest to the right on our said spectra, are the ones closest to being like just a regular old CH3 and not near anything electronegative. So that one really is going to be the one that's furthest to the right, and then this one, and then this one. And we do go across, because even though these are both CH2s, this particular CH2 is a lot closer to that electronegative bromine. All right, next one, even though it has the same molecular formula, still 3 carbons and still 7 hydrogens and a bromine, we will see a totally different structure in the spectra because those 3 carbons and those 3 carbons are equivalent because they're almost like mirrors of itself. And this is just the only one. So while that bromopropane has 3 signals. This one only has 2. All right, next one we put an oxygen in the middle. It's still electronegative, so we'd expect those hydrogens and those hydrogens, the ones that are on the carbons right next to it, to be more de-shielded. So I would say this is going to be the lowest, followed by this one, followed by this one, but we do get 3 signals. But this one, left and right, are mirrors of each other. We only have 1 peak. And same thing kind of happened with all 9 of these. Those are all equivalent to one another because they're just CH3s right off of C that's connected to a bunch of CH3s. They're all chemically equivalent. But this other one, because it's separated with this O, is going to be different, giving us 2 peaks. I said 2 there, that should be a 1. All right, give these a try, check out your answers, and I will just go down here and mark down what they are, and if you're having some challenges, go back and see if you can figure out what's going on with it. So I have 2, 2, 1. These are all equivalent, so it's 1. And this is a weird one. Technically, this thing being totally opposite, that nitro group will be totally different than these 2, which are closer to it, and these 2 are there right next to it. So that's going to appear to have like 3 different signals. But I'm going to put a little star there because we're going to see something else affects that one here in just a second. Okay, now also something we can see in that individual, that first little thing, is that if you noticed on that, some of those peaks are taller than the others. All right, now the height of the peak is related to something, but it's better to relate the area under the peak or the area under the curve, because that area under the curve is definitely proportional to the number of hydrogens it's taking up. So the reason this is the shortest one, and more importantly, you notice how it's about 2/3 the height of this one? Well, that is because this represents just those 2 hydrogens, yet this one represents 3. And then we can see that even more. See how this is 3 hydrogens, but these are 9? If you notice, this tall peak is about 3 times the size of that smaller one. Now, on the actual height of the peak, it is generally safe to say they're close on those layouts. But when we actually look at this and describe it and try to figure how close the intensities match up with the number of hydrogens in there, it is better to look at something we're going to call the integral trace, which really is a computer way of calculating the area underneath the curve. And like this one, if you notice, this is 2 spaces for every 6, or this is a 1:3 ratio. So for every 1 of these protons, we get 3 of these. And that's what happens. If this one turned out to be a CH3, 3 times that, there are 9 hydrogens there. And this works always, regardless of how complex it is, we could always figure out the number of hydrogens. All right, so let's figure out how many hydrogens are in this molecule altogether. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And yet, from start to finish, our integral trace goes up just by 6. So that really does tell us that each one of these peaks represents double whatever this value is. So since that was 0.5, this represents 1 of these hydrogens. This one is actually 2, this is actually 3, and that one is actually 6. And we can say that dead on tells us how many protons are in that equivalency. Doesn't tell us fully what the structure is, just tells us that they are equivalent. What the structure is doing, we're going to look at how they move up. The ones that are further to the left are more de-shielded or closer to electronegative atoms. Okay, so summary thus far, we're actually going to use, we're going to put the protons in a magnetic field and let them resonate with or against the field. As they resonate, they're going to give off a radio frequency, and we're going to measure that frequency, and we're going to see it's proportional to the amount of shielding around our particular atom. as we measure it, we're essentially just going to plot that out. And that's going to give us a spectrum for the NMR. All right, so let's look at what the recorder is. Now, we're going to do something weird. You know how we said this is actually a radio frequency? Well, we kind of need a 0 point, and we know generally where it is. But what we're going to do to guarantee it is we're going to put a very particular sample in there. Call it like a control. You're going to see on a lot of these slides it just says TMS, and we're going to explain what that means. But technically what TMS is, it's a very, very shielded, it's a molecule with very, very shielded hydrogens, which is why it's almost always the highest frequency you can find. And then as we put it near electronegative things, it shifts down. Now this peak will be lower because that particular hydrogen is close to an oxygen, and oxygen's more electronegative than carbon. And these three, it will be a taller peak, but they're near a carbon, so they are actually in a more shielded position. So the neat thing is, where it shows up on the recorder kind of tells us what that particular hydrogen is near. All right, so before we actually talk about what atoms could be near, let's actually figure out a way to do that scale. Because if you think about this, if we overthink about it, we're going to realize that that scale is related to a frequency difference. Well, if we stop and think about it, that frequency difference is going to be different based on which magnet you use, because some big magnets actually shift it more than small magnets. All right, so we're going to compare everything to TMS, which is trimethylsilane. So it's got silicon in it, and that silicon is surrounded by 4 different methyl groups. Those create very shielded protons, so it's just a great 0 point. And now chemical shifts are how far away from the TMS that we use. And it's going to be measured in parts per million. Now, what that does is does something kind of cool. So what I mean by that, so we have our lowest scale. On a 60 megahertz magnet, the most shielded protons typically show up around 60, and the least shielded show up about 600 smaller than that. So we get this difference by actually taking 600 divided by 60. And in a larger magnet like a 300 megahertz, we just see that scale goes up. But the neat thing is, this thing that we're going to call chemical shift, which is just a division of these two numbers, gives us the exact same scale every single time. In the sense that TMS is always a 0, and anything higher has a very predictable location on that ppm scale, or chemical shift scale. And what I mean by a specific location, we can actually use something like this and say, okay, here's where we're expecting things to show up. So like our benzene molecule, we're expecting the peaks for a benzene molecule to show up between 7 and 8 on this ppm scale, yet the same type of hydrogen off just a carbon that's single bonds is going to be down here under 1.5. Now, these aren't absolute, so I can't say that all halogens connected to a carbon near hydrogen are going to show up in this range, because they kind of actually amplify each other when there's multiple on there. What I mean by that, let's look at just methane compared to chloromethane. Now, the hydrogens on methane give us a shift around 0.2, but if we put just one chlorine up there, it shoots up almost 3 whole units. But what gets interesting, if we put 2 on there or 3, it shifts on even more. So here we got this neat thing. That particular proton off of a carbon with 3 chlorines on it, it does have a 7.2. And if we were going by this chart alone, we might have mistakenly thought that was a benzene ring. So we need to think in terms of the entire molecule, and when we do our spectra, we want to try to assign an identity every single peak on a spectra. And we're going to get plenty of time to practice these. All right, so locations of signal, darn important. Chart like this, darn important. Even so, numerical values are darn important. So we actually do expect most alkane bonds, so just CH bonds where the carbon is sp3, we're expecting those values about 1.5. But as soon as we put a halogen near it, that pops it down here and shoots it up to 3.4. If it's got an alcohol on it, so instead of an H, there's an OH next to it, that is right here. We're showing where the H is, but this O will also shift this, so that particular carbon with the CHs is going to be close to that 3.4, just like it has a halogen next to it. All right, we got to look at a few weird things. If you notice, this vinyl hydrogen is going to show up at 5.6, but what's so weird is if I put that vinyl system into a conjugated ring and make a benzene molecule, you might think it's supposed to show up at 5.6 as well because this one did, but this particular one will show up at 7 to 8. 7.2 is where it puts on average. So it adds to it. All right, remember how we said it was the electronic structure? What we're saying in this and what this kind of shows is it's not absolutely just the electronegativity on the atoms that's near it. It's how the electron cloud near it arranges itself. What do I mean by that? Let's look at that benzene ring. So in a given benzene ring, we do have a pi orbital that goes across and above, or above and below every single one of those carbons, and it does actually create its own magnetic field, and therefore its own it creates its own electrical field, and therefore its own magnetic field. Well, it just so happens that orientates itself very, very well at de-shielding those hydrogens. But if I were to take that same idea with a pi bond for just a double bond and try to do the same thing, the overlap is a little bit different, so we don't de-shield these nearly as much. So while a carbon-hydrogen bond in a aromatic ring shows up 7 to 8, and this particular one is a great example of just benzene and what it would look like. If I were to go to just a vinyl position, like just any old alkene, that's going to shift that down more to between 5 and 6. So it's not nearly as de-shielded as the benzene ring is. It's going to help us identify and separate the two. All right, along with that, acetylene, which you might think should be higher than alkenes, is actually lower, but that's because of the orientation of that induced field. That field goes down through the middle of the bonds, leaves this hydrogen a little bit more exposed, and the electronegativity is not helping us. So we're back up to a 2.5, so much more shielded. And that's what they're showing here. This is just an alkyne, and we're seeing that peak for that particular bond. Now, aldehydes do something similar, but it's going to be a little bit more pronounced in the de-shielding. Has a lot to do with the fact that this is a very electronegative bond towards the oxygen, which helps pull some of those electrons off this hydrogen, and that de-shields us. We go down all the way down below between 9 and 10, and carboxylic acids do it even more. So carboxylic acids have that same feature, but now we have an O directly attached to that hydrogen, and we actually have to change the scale. Most of these are going to occur around a ppm of 12. Now, the graph here is kind of, think about this as being a little bit old school. So if we had to go back long enough ago that you bought pre-colored slides, so the chart would have actually been pre-done and then you put those in like a letterhead and it prints out the slide. Well, if you were doing that, it would have almost always put the 2.5 in an outset because 12 is over here off my page. Modern day instruments, they just print the whole thing from the get-go, so having it show 12 is a piece of cake. You just change the scale on the x-axis. But your textbook's going to show it like that's almost always an offset. All right, next thing we do before we start identifying things is we talk about other things that will split up or help us identify things. All right, what we're going to look at now is the fact that the hydrogen peaks that we see will split if they're near other hydrogens. All right, what I mean by that, let's think about a very simple alkyl group, the ethyl group. All right, now since this is off the end, I would expect this to have a peak that is equivalent to 3 protons compared to this one that's 2. And I would be expecting this to be shielded more because it's out all by itself. But depending on what's attached to this, that might de-shield this one. And we don't know how much because I didn't actually label it what it is. But I wanted to look at how these two peaks interact because this is what they're talking about on this spin-spin. Turns out those two hydrogens have electrons on them that have their own spins. And these two, heck, they might be spinning with the magnetic field, making the magnetic field stronger. They could both be going against the magnetic field and making the magnetic field weaker, or you might have a 50-50 split. And technically, if you think about the 50-50 split, you could have the first one going up and the second one down, or opposite of that. So we got two ways of doing this. Well, that influence, or that additional magnetic field, or removing, causes that peak that creates those three hydrogens to change. The splitting happens because of nearby hydrogens. And what it looks like on an actual spectra is they really do split. So since this location, which is the bigger one because it's got two hydrogens, is near this location with one, that one hydrogen either helps enhance the magnetic field or distracts the magnetic field, but that one peak gets split into two. And this one, which would have been a single peak, is being influenced by both these. So these two peaks cause this one to split into three. Now, where that 2 and 3 come from, you actually see something kind of like this when we actually focus on what's going on. So these two protons, and they're the same in both these molecules, are showing up in the spectra either de-shielded because the nearby hydrogen enhances the magnetic field, or shielded because the nearby one disrupts the magnetic field. But since this can only go with or against the magnetic field, you get one or the other and never both. So you're always going to see that effect. Now it needs to be nearby. If it's more than one carbon away, we ignore those nearby hydrogens. It needs to be on an adjacent carbon or an adjacent atom to actually cause the splitting to occur. And the one that created three peaks, the reason it did is because this one peak was either enhanced by both, the magnetic field was enhanced by both those electrons, or disrupted by both those electrons, or one enhanced and the other one destroyed, or vice versa. But this peak gets twice as high because there's two different ways it can do it. Now, you can almost always predict the peaks and the size of them using something like Pascal's triangle. You know how when these things go down, they get bigger because you add these two together. So 3 plus 3 is 6, and 1 plus 3 is 4, and 1 plus nothing is 1. So we can build this, but this is going to relate to their peaks. Now, where this gets really neat is the number of protons causing the split is always one number less than a number of peaks. So we have something like this. So if you have n number of equivalent electrons, you have n plus 1 peak. You always have one more peak than you have splits, or then you have signals. All right, so that range is affected by only adjacent locations, though. So if I have a CH3 that's right near a CH2, these two both affect each other because they're on adjacent carbons. But if I were to take that same idea, but between the two I put maybe like an oxygen, that has now moved them too far away, and these two do not split those three. So they have to be close. It's going to help us actually identify structure as much as anything, because we get something like this happen. So notice how I have a split peak and I have a split peak. Since you need them to be adjacent, we know these two locations are adjacent to each other. And this one that's not split is not near these other two, because if it was near these, it would get split as well. So we know that those are near this one. All right, so let's see if we can figure out what it is just based on what we're seeing on our peaks. All right, notice how this really tall one, and if we focus on the integral trace, doesn't it look like it might be roughly 6 times as high as this one? Well, that is the case. This does actually represent 6 hydrogens, while this one represents just 1. But they are near each other, because you see how this big peak is just split into 2? Well, that's because this one hydrogen split it. And if these 6 are splitting this one, we would expect it to be split into 7 peaks, because that's 1 more than this. And if we count, 1, 2, 3, 4, 5, 6, 7. It is 7 peaks. All right, so we have an atom where we have a fragment where this one hydrogen, which must be attached to a hydrogen, or to a carbon, is near 6 other hydrogens that are all equivalent. Well, I have 3 more spaces here, so I could either have 3 CH2s, and that would work, or maybe it is just 2 CH3s. And then the other thing is just bonded to some other thing that we're not aware of yet. Now here's the weird thing. Both those kind of fit with what we know about this right now, because those 3 CH2s would be equivalent, so that would be 6 equivalent hydrogens, and so would this. That would be 6 equivalent hydrogens. So I don't give you enough information yet to distinguish these two, but I can definitely tell that they're near each other just because they split. All right, turns out that's actually the structure. It is a CH with CH3s on either side, and that other lone one was just a CH3 all by itself. We're going to see that we have the ability to tell that with various different other skills and what we're learning with NMR. All right, I have another one of these we want to look at, just a split of an ethyl group. And I want you to try to actually figure out which peaks these apply to. All right, so the ethyl group really is just a CH2, CH3. This particular one is near a little bit more electronegative benzene ring, which is why that peak is going to be more de-shielded. It's close to that more electronegative, so it's not going to be anywhere close to that 1.3 or 1.4 that we would expect for CH2. It's going to be more de-shielded, so it's going to be a higher value, and that's what we're seeing here. And then those 3 are going to be a little bit more shielded or closer to what we'd expect just because they're farther away from that benzene. But the real plus happens when we notice that that is a quartet. 1, 2, 3, 4 peaks, and this one is a triplet. And the reason that is this triplet is being split by those 2 protons, and this quartet is being split by those 3 protons. Now, something else happens. You see how this kind of looks like a mess of things? Well, what's happening is we have 3 peaks that are definitely there because those are equivalent protons, but they split each other. And it actually kind of happens that anytime you have an aromatic ring or benzene ring, you get actual kind of random splitting unless you happen to have all equivalent protons. And hardly ever have all equivalent off of a ring unless it's the ring's all by itself. All right. Next thing we're going to notice is that the space between the peaks when they split is a consistent frequency in hertz, and it's dependent on the type of atoms you're dealing with or how they are adjacent. Now, what I mean by that on that first part, whether or not how far apart they are, the difference NMR is fixed by frequency, and it doesn't scale up with a magnet. So on a smaller powered magnet, like that 60 megahertz one I show, the splits are going to cause these things to be pretty far apart. Yet if I jump that up to 600, we see this get roughly 10 times closer. So this that septuplet that we created actually turns into a much more tight clamp, and this doublet just almost looks like a thick line. All right, now that coupling constants are a very fixed frequency, and what we were seeing as of right then was a 7 hertz difference because that's the most common on like an alkane hydrogen. They're only about 7 hertz difference. But if I actually look at the vinyl position, I get different numbers. If I look at the aromatic, I get different numbers. Well, these coupling constants can help us tell them apart because these actually interfere with each other slightly different. They don't actually cause those triplets and quartets quite as much. They create different patterns. Now, what I mean by that, I want you to focus on this HA and think about the splits it would have. We know these hydrogens are too far away, so they're not going to split it. The only thing that should be splitting this particular hydrogen signal is this carbon and this carbon. Now, when we first introduced splitting, we would say, well, it's being split by 2, so we're expecting this to be a triplet because it's being split by 2 things. All right, that would be the case if these 2 were exactly the same and created the same coupling constant. But on this particular one, The trans one creates a coupling distance of 17, and the closer one is 11. And what that difference means, we're going to see something like this. The first split, so the furthest part, causes a split of 17. But the next one splits each of these by just 11, and they don't cause the two middle ones to overlap. So we don't add these up. We would have 4 equal-sized peaks, and 2 of them are 17 hertz apart, and the others are 11. We get 11 between the first two, and 17 if you go from here to here. And if I look at HB, I get a totally different quartet, because this one split by this one at only 2 hertz, or a little bit under 2 hertz actually, or 15, or 17 I mean. So we get a very tight split, separated by a much larger one. And if we do the same thing with HC, we see even a more similar one. But all right, even though it looks like these 3 patterns are quite complex, technically they're not, because about the only time I see all 3 of these quartets is if you have a CH double bonded to a CH2. This needs to be connected to something, but that structure gives us these 3 sets of complex split peaks. All right, something else we see. Sometimes CH2s could actually react and give us stereo centers. Now, an easy example of this, let's look at just butane. Now, technically, if I were to replace one of those hydrogens with a halogen, I would create either an R or an S stereoisomer. All right, that tells us that these hydrogens are not quite exactly the same. All right, that's not only, that doesn't mean that we're going to have this weird little feature happen. The only time we have to worry about stereochemical non-equivalence is if an adjacent position is already a stereocenter. All right, let me go to an actual example where this happens. This particular molecule right here has an asymmetrical center, and right adjacent to it is a CH2. All right, this particular CH2, and only this one, has a very slightly different splitting pattern. These 2 hydrogens do not behave the same anymore, because if I were to replace HA, I get one particular stereocenter, and it would be totally different than if it's HB, but they're not enantiomers of each other. They would be distereomers. So if this was a halogen, I have almost a different structure than if this one is a halogen. All right, because of that, A and B behave independently. And that really does mean, if we're looking at that hydrogen right there, while it is split by these 2 hydrogens and those 3, this one here is actually split by this one and this one. Because even though they're equivalent, they're not exactly the same, so we get a weird splitting pattern. That's what they're showing here. We get this very nice, pretty septuplet that we're getting because this hydrogen split by those 3 and those 2. But these 2 are this guy and this guy individually. All right, what we're going to have to do before we introduce something more weird is point out that OH and NH, because of their hydrogen bonds, add a little bit of complexity to our molecules. What I mean by the complexity, if I were to have a molecule, and we'll keep it simple, like ethanol, I would expect a peak for this, and yet another peak for this one. And I would expect this one, because it's near that is being affected by these 2, to be a triplet. This middle one is going to get split by these 3 and this one. Since that's 4, it's going to make a pentuplet. I typically call that more a multiplet, because if we don't have a good magnet, we won't be able to tell that wouldn't necessarily be able to tell the difference between 5 and 7 peaks. So I just typically say multiplet. Yet this last one, that represents a single hydrogen, should only be split by those 2, making a triplet. All right, that is expected, but we see something weird happen on this last position and even this one right here. All right, hydrogen bonds are quite strong. So in that sample of just pure ethanol, we would kind of expect a nearby water molecule to make, or nearby alcohol molecule to make a very strong hydrogen bond with it. Well, it's actually strong enough that we will see certain situations where this hydrogen acts like it's attached to this one at the same time, giving us yet another thing that would actually split the peak. So we were at a triplet, we're at a quartet, and same thing happens here. It might actually split this one. All right, but it's more of a might. It needs to be nearby, it needs to be adjacent, it needs to be there, but it may or may not be there. And on anything with an OH bond, there's a possibility there's one above it, maybe a one below it. So we might have more than one H that comes in there and splits it. So in a typical NMR, any OH peak and any NH peak can look odd simply because of hydrogen bonds. So let me show you what I mean by looking odd. This is that OH peak down here. And if you notice this one, it's got a messy little scattered peak. It's not really like a triplet or quartet. We have an asymmetrical peak going on here. Yet down here, it's really nice and clear. Matter of fact, even this one, see how noisy this kind of looks? And it really is, because this one may or may not get split by an adjacent hydrogen from a different molecule. And same down below. So we get messes. Now, all we're going to do to eliminate this problem, make sure that we don't have to worry about hydrogen bonds, is typically play around with the purity. So super pure solutions of, say, ethanol, definitely create both these little patterns. But if I put something in there that's got some extra H's or O's, so water even, I actually can cause that to shift. So just put a little bit of an impurity in there and I don't get that same splitting, because all of a sudden the hydrogen bonds are not nearly as interactive. All right, we do see the same thing with OH and NH. Anything that does hydrogen bond will do this. But NH is a slower actual, or a much more moderate rate of exchange, so it happens a lot more steady, and we definitely don't get those individual split peaks. We get more of a curve based on those. They are typically broad. OHs are definitely more peakish, but they might just be almost look random on their differences. All right, so how we're going to distinguish these is a kind of a little cool technique. Now, as I always said, if you make an put an impurity in there, they move around. Well, we're going to choose a very particular impurity. We're going to actually add deuterium oxide. Now, the reason we do that is, chemically speaking, a deuterium behaves exactly like an H. So this OH could turn into an O with deuterium. This NH could turn into an N with deuterium. And chemically speaking, there's not a single thing different between those two atoms. The hydrogen behaves exactly like a deuterium. In an NMR, though, deuteriums typically are absent totally, because you have a single proton and a single neutron. Their individual spins cancel each other out, so deuterium disappears from the spectra. So what we end up doing to actually identify this, and I don't have it on here, but we're going to mention it down here. We will actually measure the sample, get either that broad peak for ammonia for a nitrogen NH bond, or a somewhat chaotic peak for an OH, and then we put the deuterium in there, and it's either going to clean it up or it's going to make it disappear. And by disappear, it really does just take and replace all those H's off the oxygen with deuterium, and deuterium never shows up in an NMR spectra. So that's what we end up doing. We measure it, see that weird peak, throw some deuterium in there. The peak that disappears is an OH or an NH. All right, last little thing, since we just finished up proton NMR, I'm going to give you a loose idea of how we go about utilizing this on proton NMR. All right, so now we're not going to fully identify this. I'm just going to go through. I don't want you to view this as just how to identify it. I want you to utilize this to identify the steps you're going to take. All right, so there are a few things we're going to guarantee that we know based on what we're giving when we're given multiple things. So first thing I actually want to figure out is your elements of unsaturation. And you would like to figure out exactly what happened to those elements, so unsaturation. Now, if we actually do this, we're going to see that this particular thing actually has 5 elements of unsaturation. And I got that by twice that 9 is 18, plus 2 is 20, and I subtracted the 10, got back to 10, divided that by 2 to get 5 elements of unsaturation. Now, the next thing I want to do is try to figure out what functional groups are present from my IR. Now, I don't need this to be perfect, but I can actually determine quite a bit of things from these two right off the bat. Like, for instance, that O is either like an alcohol or an ester or a carbonyl, and we can identify all those by looking at this peak. Matter of fact, that thing right there is a good indication we have a carbonyl. Now, we don't have to worry about being an amide or an ester or a carboxylic acid because there's not any other O's or N's. So this particular carbonyl is either an aldehyde or a ketone. And our IR spectra tells us it's definitely not an aldehyde because we don't have that 2700 and 2800. So in this case, we know 5 elements of unsaturation and we know we have a ketone. All right, now, we can point out that this is a little bit lower than we expect for a ketone, but that's acceptable. We have this other peak right around 1600, which is a good indication that you have a carbon-carbon double bond, and it's either a benzene ring because it's so low, or they are conjugated to each other. That's about the only reason both of those would be shifted. But I don't know any of that for sure. I just have those as suspicions. Now, I really do like this suspicion because those 5 elements of unsaturation, that carbonyl only took care of one of them. All right, so we have a general idea of functional group when we have elements of unsaturation. And in general, we can safely say on this one, we know what one of those elements of unsaturation is. So when we get to the proton NMR, we want to assign every peak. But we're going to do this a little bit different. Let's start by looking in our NMR for something that actually explains those elements of unsaturation. Especially when you have a lot like this one, because I would like to explain the other 4, and I can right there. The only reason I should have a bunch of peaks in that 7 to 8 range is if I have benzene. And 2, 3, 4, 5, that's a good indication. I have a benzene with 5 hydrogens coming off of it, so I just have a single substituent on it, and that would create those nice peaks. It actually takes care of all my elements of unsaturation. All right, the next thing I want to do on here, I kind of want to understand what's causing all my other peaks that have splits. The last one would be the rest of the peaks. But I don't have to worry about that because once I've actually identified the split peaks on here, the only other peak is this last one, which we know is TMS. All right, but this is nice. I have this split peak and I have this split peak, which are the only split peaks I haven't actually assigned. I know they must be near each other. This one has 2 equivalent protons in it. This one has 3. That's a very good indication. I have a CH2 right next to a CH3. And I can confirm that because those 3 hydrogens would split this one peak into a quartet, which I see, and those 2 hydrogens would split that one peak into a triplet, and we actually see that. So this seems to be a fragment. Now, if we come up here and look at the actual empirical formula, this fragment, and that carbonyl do explain all of this. So we have our 3 pieces, and this structure really is a benzene ring connected to a carbonyl, connected to a ethyl group. We've just put our pieces together. All right, but before we want to do that, we're going to add one more instrument into the mix. Now, it's not really an instrument, it's just a modification of proton NMR. We're going to look at the carbons. Now, before we say something nice, like it's just a add additional thing and you do all the other steps, we're going to see there is quite a bit different about this. The first difference comes from the fact that we can't see carbon-12. So 99% of the carbons in the universe have no magnetic spin, so they do not show up in carbon NMR. only 1% of all carbons on Earth or in the universe are expected to show up in a proton and a carbon NMR. So we're already going to lose a tremendous amount of signal strength based on that. And the other problem, the actual frequency is the gyromagnetic ratio is 1/4. So these signals are very weak. And if we tried to do this the exact same way as proton NMR, we would see a bunch of noise down at the axes and we would not see any of the carbons. So we kind of need to take hundreds upon hundreds of spectra and average them out. Oh, if we did this on our old style instruments, like those first ones I showed you, it would take days upon days to get a weak signal. So we figured out ages ago how to speed this process up, and we do this all the time now. So when we put our sample inside our magnetic field, we're going to get it resonating and get that NMR resonance going by pulsing it with a large infrared signal, not infrared, RF signal. That pulse gets our nuclei spinning in and outside of that resonance, and they're going back and forth. But it does create a bit of chaos. It actually gets them all going, and we get this kind of a weird decay. And it does actually come out looking like this. It's going to steadily get smaller because we're going to go back to a normal state where they're mostly not actually flipping back and forth. But we're going to get these weird patterns. And this thing that says FT, Fourier transform, is just a fancy math term that says we're going to turn this time-independent RF pulse or chaos into individual frequencies. We're going to analyze those patterns that are going and turn it into something more useful. And where this really comes in handy, this is a millisecond, this is a few milliseconds. This really does, and even like a carbon or NMR, we're talking about we can get a full spectra in 5 seconds or so, or a very short amount of time. So we can repeat this over and over and over, and because of that, we can isolate these things out. So I show this to show where they line up. I wanted to actually show this first. So a typical carbon NMR, because it's so easy to do proton in that machine, what they typically do is if we take 90% of the time to actually get a decent carbon NMR, less than 10% of the time will give us a much, much, much better proton NMR. So we always see them together. Now, we shouldn't say that these peaks align up because where they show up on the carbon NMR is slightly different chemical shifts. So that's why I wanted this chart to show us. So we do see carbonyls shift very, very high, just like carbonyls cause the hydrogens to shift. And we do see that benzene pop up here. But what we see different, even our double bonds are here. All double bonds show up between 100 and 150, yet before, some double bonds cause the hydrogens to be here and these hydrogens to move up here. So they do show up in different locations. The chemical shifts are far greater, but I do want you to notice also on this, the peaks are a heck of a lot different in height. All right, so let's explain some of these differences and why they happen. All right, so we're going to have to deal with that 1/4, and we are going to see right off the back that the peak height has nothing to do with the number of carbons. Turns out the intensity of a peak in carbon NMR is related to the hydrogens. So back up to this thing, this peak is taller than these two because this particular carbon, wherever it is, has more hydrogens on it than these two do. Now it's far easier to see this if I go to a much simpler molecule. So what I mean by simpler, I only have 2 sets of carbons with protons, but I only have 3 carbons. All right, this carbon here that has no hydrogens has a very small peak, yet this one with 2 and this one with 3 have much more noticeable peak. And if we did an integral trace, we would see that this is actually proportional to 1, this is proportional to 2, and this is proportional to 3. Almost dead on the number of protons attached. All right, we also don't see splitting for the exact same reason. We will see splitting, but the splitting's different. So carbon isn't likely to do spin-spin splitting based on another carbons because the only way we'd see it is if we had 2 carbon-13s right next to each other. And if you only have a 1% chance of it being a carbon-13, you have a ridiculously low chance of having 2 carbons adjacent. So they do not ever split each other because they never are near each other. And the few occasional times it does happen are too small. We actually can totally ignore any spin-spin splitting due to other carbons. However, the protons near that particular carbon will couple with it. So what happens, a particular peak gets split based on the hydrogens attached. So that same molecule, that particular peak would get split into a triplet because it has 2 hydrogens. This one gets split into a quartet because it has 3 hydrogens. So the splitting is due to the hydrogens on that sample. Now where this gets to be a mess, we have a very ideal situation here where that coupling constant is pretty darn close together. Unfortunately, what happens in a lot of the carbon NMRs at those lower frequency, these peaks get wider and they start to overlap with each other. So while we do get that same number of the number of hydrogens is 1 fewer than the number of peaks we see, we do see that we get an overlap. We got that chaos. So what we're going to do to get rid of that chaos, we're going to actually cause those protons to not so much disappear, but disappear into the noise. So since all spins are related to RF fields, what we're going to do is bombard our sample with the perfect RF frequency to get all hydrogens flipping back and forth very, very rapidly. And if they're both flipping back and forth, they can neither help nor hurt your magnetic field. They disappear. That splitting disappears. And we really do see something like this. We can run a sample with all those hydrogens not interfering for a sample, and we can turn it off and they pop right back up, and you can actually help identify things. But this actually pays off tremendously because I don't have to worry about any overlaps, because I know this peak is right there, this peak is right there, this peak is right there. And then I can turn that switch back on, let them spin, let them flip, and I can tell, all right, this has 3 hydrogens, this one has 3 hydrogens, and this one has 2. So I can use that to help identify things. Now, the last few techniques we look at just take advantage of that, because while these things are happening all the time, they actually can cause chaos because there can be a lot of peaks, so it actually can be problematic. And if I go to a sample with a lot of carbons, which is very true, happen in organic chemistry, you can get a lot of carbons, we can start to see a lot of a noise. So we're going to look at one of the clever techniques that we do to simplify that. It's DEPT carbon 13 NMR. So it is 3 repeated scans, all done to the same sample. But a great way to see what's going on. Let's look at something that's got a lot of peaks. So this is a steroid. Has all these little carbons on a carbon NMR. Look at all these peaks that show up. And if we were to try to identify those, that's going to take a long time, a lot of effort. All right, so what DEPT does for us is it splits it up. So the very first thing we do is we actually get a normal NMR, and then we do what they call DEP90, which only causes the CHs to appear. So if it's carbon without any hydrogens, or carbon with 2 hydrogens, or carbon with 3 hydrogens, it doesn't even show up there. And then our 135 gets the odd number hydrogen ones to show up positive, and the even numbers to go negative. We get something that turns this into this. So we have all of our peaks. All these are just our CHs. And now we have CH2s that are negative. And any peak that wasn't here before, that's a CH3. It helps break that up so we can identify things. Now let's take it a step further for even bigger molecules. We're going to introduce something called 2-dimensional NMR. A great example of that, if we look at this molecule right here and look at any one of these protons, we're seeing that everything splits. So even though we got these 5 different signals, each of those 5 is going to have a split aspect to it. Now it's easy to tell what's going on when it's only got a couple things that are split. But when every peak is split, I can't easily look and say, well, peak A was split by E, or A was split by B, or A was split by C. I just know that they actually were split by another one. Well, COSY, or correlated response, actually does a weird thing with the sample, and we actually cause little weird peaks to pop up off axes. That's what this little thing is. It's not actually along the diagonal or on the end. It's just this weird, we call it a cross peak. Well, that cross peak happened because whatever peak A is, it's being split by whatever peak B is. The cross peaks tell us which 2 are splitting each other. And you see how this line matches up all 3 of these? That really is telling us that whatever C, D, and E are, they are all splitting each other because they all line up with the same cross peaks. And we can take that idea a step further and do different species. So Hector basically takes something like carbon and hydrogen, and we really are seeing on these cross peaks which carbon causes which hydrogen to split. Now these last three techniques are really done for much, much bigger molecules, and while we will talk about them and such, we're really not going to analyze the data on these. And if we were to have that spin solve NMR in our lab, those techniques actually take half-hour runs or so. So it's not like this happens easily. These are really for much, much bigger molecules. Like this example right here, there is absolutely no need to do a Hector for this. You could actually get that result from just a standard carbon and proton NMR. It just would be quicker if you had a Hector sample. All right, now, don't have any examples we're going over here. What we're going to do with this is actually put this out there, and our examples we're going to do on our little online Zoom sections. All right, have a good evening.